The speaker shown below is used to produce the bass notes in music system. The cone moves with simple harmonic motion and emits a single frequency of 100 Hz. When it is producing a loud sound, the cone moves to a maximum distance of 2 millimeters. So what is that 2 millimeters? Can I say that is the amplitude? So you can write this one either by A or by X naught. It doesn't make a difference. The equation that mathematically describes the displacement at a certain instant, precisely we call it instantaneous displacement. So the equation that describes the displacement of the cone is this one. So 1.0 into, so this is the instantaneous displacement. So the amplitude is technically 0.001, because it says cone moves to a maximum distance of 2 millimeters. So it moves forward and then it moves backward, so it covers a total distance of 2 millimeters. So the one-sided distance, the maximum one, would be 1 millimeter. How do I confirm this one? Actually, I confirmed this one from the expression, because the standard expression is x equals to x naught cos omega t. So at t equals to 0, the amplitude is maximum. So the time starts when the object was already at the extreme position. Show that the data for this figure lead to the numbers in the equation above. Okay, so alright. So frequency was given already 100 Hertz. Okay, let's start off with the frequency. We know angular frequency equals to 2 pi f, one of the formula. Another thing we know is the maximum displacement, aka the amplitude, which is 1 millimeter. So the total distance was 2. It means the amplitude is 1 millimeter or 0.001 or 1 into 10 to the power minus 3. That's why they have written it over here. So omega equals to 2 pi f. So omega has to be 628. Let's see if our omega is 628. So 2 into pi into 100. Could you hit it on the calculator? 628. So can we, 628 into 3SF. We are absolutely right in 3SF. By the way, what unit do we have for this one? 628 radians per second. Radians per second. So are we clear with the expression that how do we have 1 over here, how do we have 628 over here? 1 from the second sentence, the amplitude thing, and 628 from the first sentence, the frequency thing. Are we good with this? Okay, let us move on to the next one. It says calculate the maximum acceleration of the cone. So any formula that you remember for the maximum acceleration of the cone, minus omega square x naught, or if you want to write amplitude by A. In the calculations, we don't use the negative sign because we should be aware of what the negative sign represents in pretty much all quantities. In some quantities, for example, gravitational potential energy, negative sign represents a situation. So you cannot randomly ignore negative sign over there. Here, negative sign simply means acceleration and displacement, they are in opposite direction. So we're not really concerned with the negative sign. Omega was 628. Now we take square of it. And what is the amplitude? 1 millimeters. So could you hit it on the calculator? Okay, 394.4. So can I say 394 meter per second square? The maximum speed of the cone, v equals to V max equals to x naught omega, or you can also represent by the notation V equals to A omega. A represents the amplitude. What do we get? The maximum speed would be 0.628. It is simply dividing it by 1000, or into SF you can write it as 0.63. What do you say? Then we have the next one. On the grid below, sketch the acceleration time graph for 2 cycles of vibration for this speaker cone under these conditions. Add suitable numeric scales to the 2 axes. So this is the expression for displacement. I'll use this one. 1 in cos, okay, x equals to 0.001 cos 628. So first of all, what we know is acceleration time is sinusoidal. So if I take square of this one, sorry, if I take the derivative of this one, we get velocity time, and that would be the derivative of cos would be with the minus sign. Once we take further derivative, it becomes acceleration. So acceleration would be minus cos. The derivative of minus sign is minus cos. So the graph has to be minus cos, means something like this. The maximum acceleration was 394. Okay, 394. So yeah, we can write to 400 here. So let's say here it is 400 and 400 at the top, because the maximum acceleration remains same. And time for one wave cycle, we don't know how much. So the frequency was 100. Can you find time period? 1 over 100, 0.01. Oh yeah, 0.01. So it means it takes 0.01 seconds for one wave cycle. So I can write 0 here. This, if this one is 0, then this one needs to be 0.01. So the displacement, another thing is displacement was maximum at t equals to 0, because if you put t equals to 0 here, 1.0 into 10 power minus 3 cos 628 t. So if I put t equals to 0, check it out. If I put t equals to 0, we get maximum displacement. This one would be, the answer would be this much. So your x would be the maximum x that you could have had, which is equal to x naught. So means your displacement is maximum, and we know acceleration is proportional to displacement. Sure. So if your acceleration is maximum, sorry, displacement is maximum, acceleration is also maximum, but with the negative sign. So that's why it starts, it is a sinusoidal wave, or more precisely a cosine wave, starting off with a negative cycle. Okay, so the amplitude capital A, or x naught, however you want to represent it, was 1.5 centimeter, which means 0.015 meters, and then the square of it. So 1 over 2, I can write it as 0.5. It'll be easy on the eyes, nothing else. So could you find me the value of omega from here? Okay, so we get 20.9. Okay, if you say so, I can believe on the face of it. And then you insert it all the way over here. 2 pi divided by the answer. It should be less than 1. So 0.30 seconds. So for 4 marks, probably the easiest 4 marks that you can have. But the only thing is, we need to be aware of these formula. We can find Now keep it in your mind. We can find omega not necessarily by the formula of time period. You can also find omega through the formula of energy. Can you repeat this statement? Which energy? The maximum kinetic energy, because for the maximum kinetic energy, that equals to the total energy also. But you can find kinetic energy at a specific displacement also, but then the formula would be slightly difficult to tackle. It includes minus x square also, then you need to insert a specific value of x. Anyway, let's move on to the next part. State the cause of damping. So we need to understand what the damping is. Only then we can answer this question, what could be the cause of damping? The resistive forces could be the air resistance in this case, for example. Okay, then we have a next one. A light card is attached to the object. The object is displaced with some initial amplitude and then released. So light card. So now the object looks something like this. Just try to visualize it. We have a small card which is attached to this block. Now it could look something like this. So it's not a heavy mass, it's just a card. Maybe I should draw it slightly differently. Yeah, so small card is now attached. So it'll trap a lot of air. There'll be more air resistance. The object would be experiencing more resistive forces. It'll slow down, and that would result in damping. During each complete oscillation, the total energy of the system decreases by 8% of the total energy at the start of that oscillation. Determine the decrease in total energy in millijoules of the system by the end of the first 6 complete oscillations. So how much energy is decreased or lost in the first oscillation? What percentage? 8? What do you say? 8%? So let me ask you this thing. The initial energy, so we're doing this question first by like a simple mathematics way, but then we can use a formula also. So 1 2 3 4 5, and I can draw an extra one. So what was the very first energy? The total energy, how much was that? How many millijoules? Just remember? 6.4. Yeah, so at least we remember the numbers, the digits. So 6.4 was it. It was. If it is decreased by 8%, can I say the leftover is 92%? If I don't want to subtract, then so can I say the leftover will be 92%? So now what is 92% of this number? Do it on the calculator. Okay, so 5.9 after first cycle. Now in the second cycle, find 92% of this one, because only 92% would be left. 5.4. okay, in the third oscillation, 92% of this number or this energy would be left. How much? 4.98. In the fourth cycle, fourth oscillation, 92% of this one would be left. In the fifth cycle, 92% of this one will be left. In the last cycle, which is the sixth one, 92% of this one will be left. 3.88. okay, if you say so. 3.88 is now the leftover energy after the sixth oscillation, and the starting energy was 6.4. How much energy is lost after 6 oscillations? Can I subtract them, the first one and the last one? So 2.6 millijoules. Okay, now this is a method if we are slightly below par in mathematics. We can simply use an expression. Every oscillation, it decreases 8% of that value. So we can form a general expression. The leftover will be 0.92. 92% means 0.92 raised to the power number of oscillation. So what is the initial 6.4? Only, so think about it this way. After the first cycle, first oscillation, 92% would be left. After the second oscillation, it would be, the remaining energy would be 0.92 raised to the power 2. After third one, the remaining energy would be 0.92 raised to the power 3. After the sixth oscillation, it would be 0.92 raised to the power 6. So could you give me this value for the remaining energy? So do it carefully on the calculator. 3.88. So 3.88 is the leftover energy after 6 oscillations. What is the energy lost? Do you agree with this expression? So the energy lost will be 2.56, or in 2SF you can write it as 2.6 millijoules. So if I be honest, they have linked some mathematics here, but even if a student says I was not that advanced in mathematics, we do not take mathematics, you can do it the normal way also. It'll take some time, but eventually you'll be getting the right answer. And there was a follow-up part which I have missed here, missed to print here. The follow-up part was, what kind of damping takes place with the help of this card? What kind of damping takes place? So the answer is very obvious. It is light damping. Why? Because the total energy decreases only by a small amount, 8%. So you see, even we have undergone 6 oscillations and still only a small amount of energy is being decreased even after 6 oscillations. Only a small amount of energy. If you have critical damping, if you have heavy damping, the other kind of dampings, in those dampings the amplitude decreases sharply in a certain part of the oscillation. It decreases tremendously quickly.